Okay, thank you very much, Mark, and thank you all for coming. This is meant to be more of a conversation, so people from the Billionaire workshop, please interrupt and ask questions. People from Moiré, please jump in and add anything I missed. Okay, so here's my plan for this talk. We're working in a field that we call quantum materials, so I wanted to talk a little bit about that. What do we mean by quantum materials? Okay, and the focus of our workshop is on 2D materials specifically, so materials that are 1 atom thick or just a few atoms thick. And try to motivate that. So why is that so exciting to work on 2D materials? Okay, and finally, I'd like to describe a little bit of give you a brief overview of some of the exciting physics that I think over the past several years has been coming out in this field of studying 2D materials. Two physics and new physics in 2D. Okay, so I'll talk a little bit about Moiré materials. I'll explain what these are and beyond, which is what our workshop is about. Okay, so we're studying quantum materials. Okay, so this is yes.
So how do you define quantum materials? Because isn't every material quantum?
Yes, yeah. So that's item. Right. Okay. Yeah. So that's of course correct. Every material is a quantum. What we do is we try to understand how the laws of quantum mechanics of electrons and ions basically conspire to give rise to the behavior, in particular the electronic behavior of materials. There's a lot of materials are quantum. A lot of their behavior can be understood classically. We kind of tend to focus on the aspects that are inherently quantum mechanical. But that's what we do. Partially, the name is a sales pitch. Okay, everything nowadays has to be quantum. Part of it is, of course, real. Okay, but we all know that the properties of materials ultimately are determined by the the arrangement of the electronic states in the materials. Okay, so this has been known for a century. Okay, so we have electronic bands in a material, and some of them might be filled. This is the so-called Fermi energy, and we fill these states up to the Fermi energy, and the arrangement of these electronic states and how many of them are filled and how many of them are empty, this is what would determine what this material would behave like. Okay, so we know that metals, insulators, semiconductors, now we know that there are more options, okay, and they're actually quite exciting. Since the last couple of decades, we know that we can have topological insulators. In a magnetic field, we can have quantum Hall states. I'll talk about these a little bit later. Okay, but all these behaviors are ultimately a property of the quantum nature of the electrons. The arrangement of the electronic bands and where the Fermi level is would determine all of this. And needless to say, we all know what a technological revolution understanding this part has led to in the last 50 years. Okay, so that's really one of the big triumphs of our field. Okay, and Beyond this, okay, what we know is that electrons interact with each other. Okay, so electrons are not independent particles. Nevertheless, some of the properties of materials can be understood from an independent electron approximation. Okay, basically all the list of these phases of matter. Nevertheless, there are strong interactions between electron and a material, and once electrons interact with each other, that can give rise to new emergent properties that are radically different from those of independent particles. Okay, and that's actually one of the main focuses of our workshop, exactly on these states of electrons that cannot be understood from an independent electron approximation. Okay, so interactions between electrons. Okay, so this can lead to all kinds of exotic behaviors that are not listed here on the left. Some of them more familiar, ferromagnets. Okay, the spins of all the electrons can behave as one collective degree of freedom, one giant spin, and that's on our fridge. Okay, so that's familiar from everyday life, but this is a quantum many-body effect. Superconductors that I'll talk about is another example of this. Fractional quantum Hall states. Okay, quantum Hall effect is another example of such a quantum many-body phenomenon. And the list goes on. Okay, so these are phases that are much more interesting. They're much harder to understand because to understand these states, we really need to understand the many-body quantum physics, which of course is a very, very difficult problem, and that's where also all the excitement and the surprises come from. Okay, this is where theory struggles to make quantitative predictions, and experiment gives new surprises all the time. Okay, so this is what we do. We try to expand this list. We try to refine the understanding of these phases. Okay, we know that now, as of the last 2 decades, superconductors can also be topological, and they can have exciting properties, and so on. Okay, but understanding where do these states occur, how to realize them in the lab, what their properties are, how can they be applied, this is what we do. Okay. All right, so that's quantum materials. Now, why do we want to go to 2D? Okay, so this is really a direction that there have been yes, please.
So I was wondering what determines whether a material reaches a regime where the interaction between electrons are important. Is it like something external like temperature or magnetic fields, or is it something intrinsic to the property of the material?
Yeah, yeah, great question. Okay, we'll look into that in great detail in the following. Very loosely speaking, there's a dimensionless ratio. Okay, so an electron in a metal has a finite kinetic energy, which is the Fermi energy. Okay, because of the Pauli exclusion principle, the electrons that are responsible actually to the low temperature behavior of a metal are moving extremely fast. And it's the ratio between that kinetic energy and the typical potential energy between 2 electrons that would determine how important interactions are. Okay, very broadly, of course, lots of other details. Yeah, but I'll come back to that point in great detail. Okay, so yeah, great questions. Any other questions or comments? Okay, fair enough to call these quantum materials? Good, right, great. Okay, so why do we want to go to 2D? Okay, so our dream is to design our materials. Okay, so there are materials that are found in nature. There are materials that are fabricated in the lab. When we want a new material, okay, so we want to have a material that would be a metal and at low temperature would become a ferromagnet and a superconductor, and if you apply a magnetic field would become a fractional quantum Hall effect. What do we do? Okay, so 20 20th century physicist would go to their chemist friend and ask them, these are the properties that I want. Okay, we're kind of bound to the periodic table. We're at the mercy of the periodic table. Now, we have the combinatorics of the periodic table. There are infinitely many compounds one can form, but nevertheless, that's our playground. Okay, so now, I don't know if you talked a lot to chemists. Chemists are great. They would cook up whatever you want. Okay, so it's really wonderful, but we're physicists. We don't want to learn chemistry. It's complicated. Okay, we want to be physicists, and we want to design our materials according to our principle, not the chemistry. 2D allows us to do that. Okay, and that's the key insight, which I think has been really driving our field for a long time. You have a 2D material, and I'll discuss one in particular, graphene, of known properties, but now you can create a new material just by stacking another one on top of it. It can be the same material, it can be different materials, and they would interact quite strongly. Electrons would tunnel back and forth and interact between the two materials, and you have new degrees of freedom that you don't have in bulk 3D materials. For example, you can place the two materials on top of each other with an angle. This is a new material, okay, and we'll look at what this does. You can change the density of electrons, a knob that's hard to do in bulk materials. Simply place a metallic gate below and apply a voltage between these two materials. Basically make your 2D system one plate of a capacitor. You can continuously change the density of electrons in this material. Okay, so that's something that's hard to do, as you know, electrostatically in a bulk material. You can do it in bulk materials simply by changing the composition. That's called doping. Okay, but doing that changes a lot of other things. Among other things, it changes the chemistry of the material. It changes the disorder potential that an electron moving through that material would see. Okay, this is a fantastic way to control the carrier density. It's nothing new. It's actually a field effect transistor that exists in your phones. Okay, but as a tool to study physics, it's really a great tool, which is only available in 2D.
Sorry, so this is a single layer of atoms, basically?
A single or a few. Okay, I can have several layers. Every composition like that would give me a new properties. And because it's so thin, I can gate it. Okay, so I can really modify.
Let's say that you consider the limit where the distance goes to zero.
Yes.
Put in,
Yeah.
I understand that maybe it's a little bit organic, right? Because there is atomic size, whatever.
They can be made very close.
But
Yeah.
something should depend on this, right?
Absolutely, yes. Great question. So, and this is again a knob that's only available in 2D. We think about electrostatics. We have electrons here. If there's a metal nearby, there are going to be image charges, and these image charges would screen the interaction. So here's another great knob. It's a tunable interaction strength that depends on the distance to this gate.
Yeah, but there is no limit where kind of it's a one layer, right? Because if you are taking distance to go to zero.
Yeah. So what you can make it extremely close if you put a good insulator in between.
Yeah.
Right. You don't want your electrons to just tunnel into the metal. Then the material is not 3D anymore. Okay. But you can play games. You can have another 2D material which is insulating. Okay, and then you can make the stem extremely close. You can make this just a couple nanometers away. Okay, so tunability, okay, is really the key. And this is what 2D allows us. Okay, and there are other advantages. For instance, in a 2D material, you can probe it in a way that's hard to do in a 3D material. You can have some kind of probe coming from above. Okay, and getting very close to the surface and really watch and see what the electrons are doing. You can image electric fields or magnetic fields very locally, or even just try to tunnel electrons in. This is STM, and see what the electrons are doing in real space. Okay, so all of this is really a great arena to study all this quantum many-body physics in 2D. Okay, so that's.
Like I would think that, let's say that we start from 3D system, and then would say that we can keep require one dimension.
Yes.
The third dimension.
Yeah.
Then, I mean, I can start from.
Right,
Okay,
right,
well,
right.
But what you're saying, it starts from some.
1 atom thick. Yeah, yeah. Yes. So the history of this field, of course, it didn't start with monatomic systems. It started from what we call quantum wells. So you construct a 3D material, but the composition of the material is changing as a function of distance. So there's some crossover as a function of thickness from 3 to 2D. This turned out to be more fun. Okay, but it's the same strategy. Other questions? Okay, so now I'm going to follow more or less historically, starting from early 2000s. So there's a magic material that really played a very big role in all of these developments called graphene that you've probably heard about. Okay, so graphene is just a single layer of graphite. Okay, so graphite is a stack of a honeycomb lattice of carbon. Okay, and a graphite is just so this is a 2D sheet, honeycomb lattice of carbon atoms. Graphite in your pencil is just a stack of many of these layers on top of each other. The bonds within each layer are extremely strong, but the bonds between layers are weak. These are van der Waals forces. So it's been known for a while that you can cleave different parts of the graphite crystal from each other relatively easily. It's very hard to tear it in the plane, but very easy to peel it off, to peel layers off. Okay, and as you know, carbon appears in nature in many structures. This is one of them. Diamond is another. You probably know, kind of a fun fact. What is actually the ground state of carbon? Is it diamond or graphite? Diamond? Yeah, it's actually graphite, it turns out. Yeah, if you just put your diamond and wait for, a couple of billion years, it will just return into its natural form, which is just graphite, is in your pencil. Okay, so these weak bonds between the graphite sheets is, of course, what makes your pencil work, but it also allows you to isolate a single layer of this material quite easily. Okay, so now physicists have noticed for a long time that if you just solve the quantum mechanical problem of an electron moving on the background of this kind of potential of the honeycomb lattice, something quite extraordinary would happen. Okay, so as you know, if you have a free electron in vacuum, its dispersion, energy as a function of K relation, would be parabolic. But if this electron is moving in a periodic potential, its effective dispersion would be radically modified in general. Okay, and the prediction was, this is a calculation that a little-known physicist did already in 1946. The prediction was that electrons that are moving in such a lattice would actually have a linear dispersion, and in fact would be described, rather than by the Schrödinger equation, by a Dirac equation. Okay, so what we will have, we describe the dispersion of electrons as a function of momentum. Now it's a 2D system. So we have two components of the momentum, and we have the energy that depends on a momentum. And the prediction is that at low energies, close to the Fermi energy, the dispersion is actually Dirac-like. Okay, so it's a linear dispersion. All the states up to here are filled. In fact, there are two copies of this Dirac dispersion centered at two different momenta. These are called valleys and would play a role later on. Okay, so this is what the low energy dispersion looks like. It looks like a cone. Okay, so and of course at higher energies, this is a band, so it connects.
I'm sorry, are X and Y the spatial dimensions, or what are X and Y?
Yeah, spatial dimensions. Okay, so these are the momenta, actually quasi-momenta in the X and Y directions. Yeah, yes, particle moving on the plane. Okay, now this sounds very interesting and very unusual. Okay, so a slow particle that's moving at the speed which is 1/300 of the speed of light is mimicking the behavior of a relativistic particle, massless particle actually, nearly massless, yes.
So in the relativistic Dirac equation, you have like particles and antiparticles.
Yes.
Which
Yeah.
an analogy over here.
Yes, particles and holes.
The electron holes.
Yes, precisely, yeah. Fermi level is here, okay? What are the excitations of the system? You can add a particle here. You can take out a particle from there and create a hole. It's an exact analogy, yeah, okay? Everything you know from your relativistic quantum mechanics textbooks would happen here.
But there's there's electrons and holes even in semiconductors, right?
Yes, yeah.
Is there a fundamental difference between these?
There is, yeah. The fact that it's gapless, okay? So in a semiconductor, there would be a gap here. In fact, the prediction is that in graphene, there's a small gap here. It's just so small that very, very hard to observe. Okay, so yeah.
But it is still speed of sound, right? It's not the speed of light.
It's not speed of light. It's not speed of sound either. It's somewhere in between. It's
Too much far from the speed of sound, right?
no, it's much higher. It's yeah, three orders of magnitude higher than speed of sound. Yes, yeah. So these are electronic speeds, not ionic speeds. Yes, yeah. It's the mass of the electron relative to the mass of the ion. Yeah, that's the factor. Yes. Okay, but still, yeah, it's basically 1/300 of the speed of light. That's the characteristic speed here. Okay, so interesting problem, fascinating material. Nobel Prizes have been given for this discovery. Interestingly, the breakthrough was to actually be able, of course, to isolate a single sheet of this material and build a device out of it. That's a whole talk, and I won't go into that. Just mention, of course, the famously the technique to do it is Scotch tape. Okay, you just peel off with the Scotch tape on there, and just deposit that on the substrate. But that's not the main. That's the main hero, but it's not the main story. Okay, so in graphene, it turns out that electrons are moving very fast. Okay, 1/300 speed of light. They don't feel each other very much. Okay, interaction effects are actually not that strong in graphene. And that's basically because of the reason that we talked about just before. Okay, electrons zoom past each other so fast that they hardly have time to interact. Okay, that's a sort of simple picture. And of course, what we'd like is to make this our playground for all this interacting electron phenomena that are much richer and much more interesting. How do we do that? What we'd like is to have something, a material like graphene, two-dimensional, but we need to somehow slow the electrons down. We have to bring this very fast motion almost to a virtual stop. And how can we do that? Okay, so this is where Moiré comes in. Okay, so there was a trick that was actually predicted theoretically about a decade ago, and a little bit more than a decade ago, and realized experimentally 5 or 6 years ago, that allows us to do exactly that. Okay, so what we do is create an artificial material, okay, where the graphene is our building block. One layer of graphene does whatever it does, but we can use that as our building block and try to design a new material with a totally new lattice spacing and totally new dispersion just by combining different layers of graphene together, stacked on top of each other. Okay, and there are different ways to stack. So if I have another layer of graphene and put it on top, I can put it with a relative shift, I can put it with a relative angle, or I can do both. Each one of these, due to the tunneling between the two sheets, would behave like a totally different material. Okay, and I can try to study whether I can design a material of my liking. And here I want to talk a little bit about Moiré, and there's some pictures that are too hard to draw by hand, so I'll show them with the projector. Yeah, so what's a Moiré pattern? Okay, so a Moiré pattern is basically what happens if you take two grids that are similar but not identical and put them on top of each other. Okay, so if either the periodicity or the angle or the precise shape is slightly different, you'll see this emergent pattern that has a length scale which is much longer than the length scale of the underlying grids. Again, these are some examples of this. So looking at up online, it's a well-known phenomenon in photography and video. Okay, so the reason is you have a shirt with stripes, and you have your camera that has a resolution. If these two periodicities are too close, you'll start seeing these funny long length scale pattern emerge. This is just beating. This is just beating between two periodicities, and it can be very long and very annoying. All the discussion in photography is how to get rid of this thing. Okay, and the most naive way is to blur your pattern, and you'll get rid of it. We don't want to get rid of it. We want this. Okay, so here's a graphene sheet, and what happens if we put another graphene sheet on top? Okay, so if it's the same angle, we can shift them relative to each other. They would want to find a particular shift would be the ground state. There's some energetically preferred stacking, like in graphite. Okay, the different layers are aligned. But if we just put it on top in the lab, we can also twist them relative to each other, and we'll get a Moiré pattern. Okay, and the smaller the angle, the larger the period that we'll get. Okay, so this is what it looks like. So here's two honeycomb lattices with a small shift relative to each other, and hopefully you can see this kind of new periodicity. Okay, so this region is a region where the atoms of the two lattices are almost on top of each other, and then they go out of registry and come back, and go out and come back again. Okay, so this is the Moiré pattern. It's a new lattice, new material, where we can control the lattice spacing. Okay, which is something that we can never ever hope to do in the real material. In the real material, the lattice spacing is completely given by fundamental constants. Okay. Now, it's a really interesting counterintuitive form, but of course there's a beautiful mathematics describing this. Very strictly speaking, this is not periodic for a general angle, right? If you just choose an incommensurate angle, the pattern never repeats itself. It's actually not a crystal, it's a quasi-crystal. Okay, but looking at it from afar, hopefully you can convince yourself that it's almost periodic, when the angle is small. It's very hard to tell whether this is exactly aligned or almost very approximately aligned, and so is this region, and so on. Okay, so to a first approximation, for small angles, and for small angles only, this behaves almost as if it's a periodic lattice.
Is this a magic angle?
Yeah, I'm going to get to that in a moment. Okay, so this is just some general angle. It would look like this whenever the angle is small. Okay, the only thing that would change as we change the angle is that the periodicity would change. Okay, I'll talk about what's the magic angle in a moment.
Is there a formula for that?
Yes, there is. Yeah, I won't show it, but I'll say it in words. The magic angle, I'll already say, is not something geometric. Okay, it's not purely geometric. Okay, but yeah, but just in terms of pattern itself, there's a sort of really nice to stare at this and try to understand how this behaves. The way to understand it is the following. Well, the angle is really small, so locally over some region, mostly it looks like two layers that are at the same angle, but just shifted. And as you go far away, the shift is changing as a function of position, and it's changing according to this formula. Okay, so D of R is the local shift that you would see as a function of displacement, and it will go from 0, means a line, to some value, some fraction of the unit cell, and then back.
In this picture, the rotation around the center mass, where's the rotation?
Great question. Okay, so yes, great question. So suppose that I assume I start by putting the atoms on top of each other with 0 angle. That's my reference configuration, and then I do the twist. I can do something else. I can start with respect to this configuration and then do the twist. Now, it turns out that for small angle, the behavior would be almost the same. Okay, it doesn't actually matter. If I have more than 2 layers, then it would matter. Okay, it would matter a lot. It would change the properties completely. Okay, but there's something special here about 2 layers only. Okay, so then you can play all kinds of games. You can ask, well, what happens if I shift? Which is like changing the rotation center. So what happens if I start shifting the red pattern compared to the blue pattern? Okay, suppose I shift it up. So what do you think would happen? No, so yeah, we shift. The angle doesn't change. The period is only determined by the angle. Right, so it's kind of really fun. It's really counterintuitive. We can do a little PowerPoint experiment here. Okay, good. So what are the electronic properties of electrons that are moving on the background of this kind of artificial lattice formed by the Moiré pattern? Okay, so we get a new material. We get a whole new material, and this is where the magic comes. You really have to solve the quantum mechanical problem of electrons moving in this large-scale lattice. Okay, this lattice can be 100 times longer than the distance between carbon atoms, and the prediction it was about 12 years ago that there's going to be some special value of this angle. Okay, so this twist angle of about 1.1 degrees, where if you look at the dispersion, which is modified by this artificial lattice, that dispersion is going to be radically different. Okay, so what actually happens as you do this? Okay, so you start from the Dirac dispersion of the individual layers, of the two individual layers that are slightly displaced in momentum space because of the small angle. Okay, and then they disperse, and then they hybridize with each other. Okay, there's some avoided crossing here, and so on. As you make them closer together, this point would become lower and lower in energy. And if you think think it through, okay, what would happen is that actually this dispersion would become narrower and narrower in energy as you make these 2 points close. And the prediction was there's going to be some angle, which is this angle, where you're going to get almost completely flat dispersion. Okay, so what actually sets this magic value of the angle? Okay, where does this number 1.1, where is that coming from? Okay, so it turns out that number is just coming from the ratio between the strength of the tunneling between the two layers and the speed of electrons within each layer. In fact, this is an interference phenomenon. Okay, you can think about it like this. Okay, just to understand where the number comes from, you can think about it very, very simply. You have your two layers. They form this Moiré lattice, large-scale Moiré lattice. There are two time scales in the problem. There's one time scale, which is the time scale that it would take an electron to move with the speed of the original Dirac dispersion from one lattice point to the next. And there's another quantum time scale, which is the time that would take for the same electron to tunnel to the other layer and tunnel back. Okay, which depends on a totally different parameter. It's the height of the potential barrier that the electron has to tunnel through when tunneling between the layers, not within the layer. When these two things are resonant with each other, that's where the magic happens. Okay, so this is ultimately where this number 1.1 degree is coming from.
And if you rotate a little more, it winds up.
Yes, very, very rapidly, in fact. Okay, so you go just a few tenths of degrees, this width would shoot up in both directions. Okay, so that was the prediction. Now, two interesting things to note about this prediction. Okay, so the first one is if this were to happen, coming back to this question about when do interactions between electrons matter, okay, so this means, this flatness of the electronic dispersion means that the characteristic speed in which electrons move is becoming very, very slow. In fact, there's a very nice ideal limit where this would be mathematically flat. Then electrons just don't move at all. Okay, so they feel each other as strongly as they possibly can. Interactions are going to do something here. Something would have to give. Okay, so interesting things would happen. And the prediction from theory, from the UT Austin group, was do this, put the two layers on top of each other at 1.1 degree, something interesting would happen. We can't tell you what. Okay, we can't solve the many electron problem. We can solve one electron at a time. Here we have, 100,000 electrons. That's too hard. But these electrons would do something interesting. We guarantee you. Okay, it can't possibly be boring. Point number one. Okay. Point number two, which is interesting, is that there are many, many things that can go wrong here, and this is why this was considered too hard to do. Okay, back in 2011, what was predicted, okay, how do you control the angle to such a fantastic level, okay, 1/10 of a degree? When you put these two things together, okay, these are monatomic layers, the atoms are not rigid relative to each other, they move around, okay, so if you put these two layers on top of each other, the arrangement of the atoms in each layer is going to change, okay, this is lattice reconstruction. This model is probably too naive. Okay, so there were many, many reasons for this not to work. So it's really marvelous that it does work. Okay, so the experiment has been done. Okay, so a few years back in the MIT group, and what happens is that when you tune close enough to this magic angle, and then tune the electronic density, the behavior of the material looks nothing like the independent electron approximation. It actually goes from being a semi-metal to being an insulator where it shouldn't be an insulator. So it becomes an insulator even though the band should be only partially filled and not filled. And then it becomes a superconductor and back, okay, back to an insulator and back to a semiconductor. Yes?
So when it becomes a superconductor, like what's the temperature difference?
Yeah, low, about 2 degrees about Kelvin, very low. We'll talk about that in a bit, okay? But all the characteristic energy scales in this problem are low. Maybe scaled correctly, this is actually a very high temperature, but we'll get back to that. Okay, but big surprise. Really, nobody expected either of these behaviors. Especially the superconductivity was a surprise and still is. But that's the experiment. Okay, so now there has been many developments since then. I want to touch upon some of them. Okay, so this system is marvelous. It's very hard to control. It turns out, if you look at these systems microscopically, as you might expect, right? You just put 2 pieces of nylon on top of each other. They crample and they bend and do all kinds of stuff. The system does that as well. The angle is not uniform. The angle is changing as a function of position, and it can fold and form bubbles in different places and so on. It turns out that there are systems that also based on these graphene sheets that do interesting and in many ways similar things without the twist. Okay, and this was pioneered here in UCSB, Andrea Young's group. Okay, so we knew for a long time that in graphite there's a favored stacking of the different graphene sheets where the different sheets align relative to each other in a very specific way. Okay, but there are always defects. Sometimes you have a stacking fault where it actually aligns the wrong way and then it goes back. Okay, and yes?
I wonder that you kind of, when you introduce this quasi-particles, whatever was the first stage, right?
Yeah.
Okay, they have kind of, say, put this below,
Yes.
the special dispersion relation, whatever. When you consider this listed material,
Yes.
you still have a notion of this quasi-particles?
That's, yeah, to a large degree, that's an open question. You know, when the angle is not too close to the magic angle, yes. But does the notion break down somewhere because the dispersion is so flat?
Yeah, right, but then, I mean, when we talk about particles, we can discuss what is the size, how fast it moves, whatever.
Yeah.
And I'm not sure that in the way you represent it,
Yeah.
something remains from the quasi-particle.
Not obvious. It's not obvious at all, right? So, yeah. So I would say the quasi-particle is some emergent property of the many electron system. Okay, it somehow means that it's still sort of smoothly connected to the weakly interacting system, and it's not obvious at all that this would be the case here. Okay, and there are arguments. There are sort of phenomenological arguments either way, I would say. Right, so it turns out that much of the same physics you can access just by stacking, without twisting, stacking graphene sheets on top of each other. Okay, so now no twist, especially if you do it with more than two, even though much of the physics appears already at 2 layers. Okay, so you find graphene sheets that are not aligned in a natural way, or aligned in a metastable configuration, and then apply a strong electric field, perpendicular displacement field, which polarizes the electrons mostly to one of the layers. So now there's no Moiré lattice, there's no big length scale. Okay, the only length scale in the problem is the distance between carbon atoms. But nevertheless, if you look at the dispersion due to interference effects between the different layers, you can get a energy momentum relation, which is again very flat. Over some range of momenta. Okay, so if you create a wave packet somewhere here, it would stay there. It would disperse, but it won't propagate. And again, interaction effects are expected to be very, very strong. And then you tune your density of electrons by a gate, somewhere to here or to there. Okay, and the electrons interact and form totally new states, including superconductivity. Okay, so the same class of phenomena can actually appear now, we realize even without the twist. And these systems are much cleaner, much more uniform, and simplify our life. I'm a theorist, my life in particular, they simplify a lot. Okay. So yeah, so I don't know if I should stop or talk for a couple more minutes or.
5 more minutes.
5 more minutes. Okay, yeah. So what I'd like to end with, just to yeah. So that's what we do. What I'd like to end with is just an overview of all the surprises that I think this system has produced. Okay, over the last decade, in particular 6-7 years. I think to a large degree, for me personally, and I think for many of us, it sort of rewrote the rules of condensed matter physics. Really lots of things we didn't expect. And I'd just like to highlight a few of them. Okay, so breaking the rules. Of condensed matter physics. We did this in many ways. So an old surprise, maybe not such as a surprise in retrospect. Okay, so 2D crystals shouldn't even exist. Okay, no 2D crystals. Okay, very well-known result from statistical physics. Okay, we can't break a continuous symmetry in 2 dimensions. Thermal fluctuation would always destroy long-range order. So how do we even talk about 2D materials at finite temperature? And yet, here they are. Okay, so ultimately the reason they exist is that we're always talking about finite systems. Okay, and the system is just not big enough to see the effects of these fluctuations. These crystals are rigid enough such that over our length scales, this doesn't show up. Okay, so if we have a material that has a tiny concentration of electrons, okay, so if we think about either of these 2 materials, the distance between 2 electrons is hundreds of times the lattice, the spacing between the atoms. Okay, so a low carrier density materials, systems with very low density of electrons, shouldn't superconduct. Be superconducting. Okay, so there are many ways for this. We would say, well, if there are no electrons, clearly this is not going to be a superconductor. The mechanism which is most well understood how superconductivity occurs is due to interactions of the electrons with the ions, so-called electron-phonon interaction. And for that mechanism to work, it's crucial that in an irregular material, the phonons, the lattice vibrations, move much, much more slowly than the electrons. But here we slowed down the electrons so much that the two speeds are actually comparable to each other. Okay, so all of our textbooks on how superconductivity works are basically out the window. Okay, this is, I think, one of the reasons why nobody ever thought that this would be superconducting, and we're still arguing it out. How can this happen?
But you mean that there is no Cooper pairs, for example, right?
There probably are Cooper pairs. The question is what binds them together. Okay, so yes, yeah. So usually it's exchange of lattice vibrations that binds the Cooper pairs together. There's a lively debate whether this is the case here or not. Yeah, yes, the Cooper pairs definitely have to be enormous. Yeah, but what are the sizes is another open question here. At least, of course, the distance between electrons could be much longer. We call the Hall effect. Okay, what's the Hall effect? It's discovered in the 19th century, okay, and a very useful tool in condensed matter physics. If you take a piece of conductor and drive a current, you'll get it, and you apply a magnetic field, you'll get a transverse voltage. Okay, that's just Lorentz force, nothing exotic. Okay, and that's very useful. The sign of that effect actually depends on the sign of the charge carriers in the system, whether they're electrons or holes. But to get this transverse motion, you need a magnetic field, right? Clearly, you need the Lorentz force. So no Hall effect if there's no applied field. Both of these classes of systems actually display what we call the anomalous Hall effect, which basically means that you see this transverse voltage, which is associated with the deflection of the electrons, even though you didn't apply any magnetic field. Okay, so the electrons are moving with no external magnetic field, and yet they move as if they're seeing some kind of imaginary magnetic field. Okay, so a mind-boggling phenomenon has been known for a long time. Okay, so the anomalous Hall effect has been known for many decades.
Can you call it emergent magnetic field? Or?
Yes, pseudo-magnetic field, yes, yeah. So it turns out that in some of these systems, you can see even the quantum anomalous Hall effect, okay, which means that you get into the regime that you usually associated with an extremely high magnetic field, where if you recall your undergrad or graduate quantum mechanics, the electrons form Landau levels, and you fill some integer number of Landau levels, and that quantizes the value of the whole coefficient, okay? And you can even see that with zero external magnetic field, and even more recently, you can see even the fractional quantum anomalous Hall effect, both in graphene-based systems and in 2D systems based on different materials. Okay, so this is literally a discovery from a year or two ago. And finally,
an effect of boundary condition that effective field appears because you have a special boundary condition and you have this sensitivity to the edges.
It's actually not the edges, it turns out. It's the bulk. So what happens is that we talked about the valleys. The electrons, due to interactions, don't like to fill the two valleys symmetrically. And the two valleys are like orbital moments. The two valleys have opposite orbital moments. And they all choose one valley or the other spontaneously. It's like a ferromagnet, but ferromagnet, orbital ferromagnet, not spin ferromagnet. And ultimately, that's what's giving rise to this phenomenon. You break T invariance, exactly. T and mirror symmetries spontaneously. Finally, and this is literally news from a couple weeks ago in our conference. Okay, so surprising to find superconductivity in the system, surprising to find orbital ferromagnetism. There's no way on Earth that an orbital ferromagnet like this would be a superconductor. Okay, no orbital magnetic superconductors, and yet here they are. Okay, so as of just a few weeks ago, a paper appeared and was described in our conference where the normal non-superconducting state is known to fill only one valley, and yet the system superconducts. Okay, this is really contrary to everything we learned in condensed matter physics, and we're still trying to get our heads around it. What kind of properties this kind of superconductor would have, and so on, I think is a very interesting question. All right, thank you very much.
Thank you.
So I gather this happens when you stack other monolayers, not just graphene.
Yes, yes, yeah. So, of course, you know, you have the materials that you have the technology to actually isolate a reasonably clean monolayer, but there are a few other materials like that. Transition metal dichalcogenized is an example that has been very, very fruitful in these regards. So the first observation of the anomalous fractional quantum Hall effect was actually done in these systems, not in graphene.
And how much do they differ from graphene?
Yeah, they're radically different. They're very, very different microscopically. Okay, so their dispersion is totally different from this. They're actually semiconductors with a large gap. They have very large spin-orbit coupling, which graphene doesn't have. And the physics is very different, okay? But some of the phenomena are the same, some are different.
They have certain properties that graphene layers don't have.
The energy scales are, it turns out, are larger. The angles you need in order to get to this interesting physics are larger, which translates into smaller length scales in real space, which translates into bigger energy scales. Okay, so that's good for everything, yeah. So it's good for the quantum Hall effect. It might be good for superconductivity that was just discovered in these systems as well, yeah.
Yeah. So this magic angle which you mentioned,
Yeah.
how it depends on the resonance in the two time scales.
Yes.
And one of them depends on the like going from one layer to another.
Yes.
I would have naively guessed that second time scale should depend on the thickness of the layer, but
So the thickness of the layer and what's in between the layers. Okay, so that time scale can be made arbitrarily long if you put some barrier between the two layers. But here the two layers are just, you know, put on top of each other. They like to sit in a very specific distance. Okay, so now it's a very interesting question. Can you change that? Yes, you can. Just press on it. Okay, apply pressure, the two layers would become closer, that time scale becomes shorter. Yes, and that experiment has been done. The magic angle changes. Yeah.
yes.
So it's been a very long time since I studied condensed matter physics since graduate school, but my very coarse understanding of the sort of core of the problem in your field is that, of course, you can't solve the many electron problem exactly, so you use vector field theories or you use approximations.
Yes.
Right?
Yeah.
So I guess what is your feeling about what is wrong with your theory, or what is the way forward given these anomalies?
Yeah. So, right. Yeah, so that's much of what we're debating in this workshop. I think this is really the best stimulant to try to develop better approximation schemes, and that's much of what we're doing. We're discussing new techniques. Of course, solving the true many-body problem is extremely hard. We would have to have, for the foreseeable future, we'd have to have some input from experiment. It's going to be a joint effort, but we can do much better, I'm sure. We can do much better. We've been playing with toy examples and very encouraging.
It's maybe not very much the question, but I wonder about mathematical side of it that say could be special in terms of conformal loop, right? That the conformal loop is much larger, for two dimensions as compared with any other dimension. And the impression is that it's kind of this long range or whatever. It could be, but I apologize that it is a relevant question.
Yeah, no, it's a very relevant question. So coming back to this point that crystals should not exist, ferromagnets should not exist either. If you don't, if the spins can point in whatever direction they want, for similar reason, ferromagnets should also not exist, and yet you see them in the lab all the time. So ultimately, I think it all comes down to the fact that these systems are not huge. they have, there may be, 1,000 on 1,000 of electrons on each side. So big, but not infinite. And we're seeing the finite size effects. If we had a arbitrarily large system, we would start seeing these peculiarities of 2D coming in.
Yes, right there.
So how large is the gap between having this material to study it and having this material to use it for something where you would like to exploit its properties?
Right, right. So you're thinking about kind of real life applications. Yeah. So the energy scales here are quite small. Okay, so the microscopic energy scale, say the repulsion energy between two electrons, is close to room temperature in these systems, which means that you have to cool down way, way below to see any of this physics. Okay, so all these interesting phenomena, superconductivity and quantum Hall effect, in these systems require you to cool to sub-Kelvin degrees to see them. Okay, so I think we're hoping. Okay, we're doing this mostly because this is exciting physics. We're hoping to learn also about the behavior of bulk materials, where the energy scales are much larger. Okay, but we're mostly doing this for curiosity's sake. These materials, the same materials, can have applications at room temperature, not these phenomena. Okay, so but just their structure and their tunability can definitely have applications even at room temperature. Okay, so things like just the band gaps between different bands in this multi-layer system can actually lead to interesting band structure that can be useful for detection, for instance. Okay.
So here you're playing with building blocks onto two-dimensional sheets that
Right.
are given to you by nature.
Yeah.
Some years, I remember that a decade or two ago, there was a lot of talk of building 3D material or 2D materials atom by atom.
Yes. Yeah.
And that, of course, widens really.
Yes. Yeah.
How far is that going? Are people still trying to do that? Or
Yeah, people are still trying to do that. So the idea is to build a sort of a super lattice, but have it many, many layers thick, and you create a new material. Yeah, people are definitely still doing that. These materials are not as pure, so the process that you do that doesn't produce as uniform materials as this, but there's very interesting physics there as well. Yeah, it's an older topic, but it has been making nice progress.
Okay, thank you very much.
Okay.